So cute! Is that from a wedding?
Yeah.
I was going to, but then I felt like I was going to puke anywhere, and I didn't want to do that, so I'll get home.
Ursa, I like your hair.
Are you coming tomorrow?
It's tomorrow? Afternoon? What's happening tomorrow?
I'll do a video.
Oh my god!
First thing told me how
Okay, our topic today is lines and planes. No.
I was going to write chapter 4.
Sorry guys, yeah, that was
Could you actually?
Oh, you're good.
Oh,
You're
we're so close.
Because you're kinda.
Oh, that's so close. So glad they checked for the day, man.
This is actually a topic that's covered in the textbook.
Yes.
Oh,
I don't know, it's like 14 or 15 or
I wrote that
something.
down.
It's
14.
Yeah, 14 sounds good.
What's the date?
It's actually in the textbook,
Second.
so, and so what that means, 13.5 in the actual,
That means you can
Someone
homework.
asked you to come sign the contract.
So what that means for us is we're kind of transitioning into the part where we're doing more traditional multivariable calculus stuff. All the stuff we did with matrices and vectors is things that I taught last year, but last year I taught them sort of as they came up because everything that's in the book I generalize to higher dimensions. And so when I needed matrices and vectors last year, I just would do a little lesson on it. So what I did was I pulled that all at the beginning so you guys at least have some familiarity with basis and rank and determinants and linear transformations and all that stuff. So I'll, for a while I'll be sort of following what's in the book, but everything that's in the book I'll give in more abstract, more general terms. And we'll use the matrix and vector notation that we developed. But this is pretty much straight out of the book in terms of content. So lines and planes. And I'm going to start with a simple 2D example that allows for one problem. Let's say we wanted to take a line through 2, 3 and 11, 5. And of course, we could all do that in point slope form. Y minus 3 and x minus 2, and the slope here, delta y over delta x, is 2/9. And if I want to put this in standard form, I can multiply through by 9, get 9y minus 2x is 27 minus 4, 23, 24. I wrote 24 because okay. So how can I do this in 3 dimensions, or 4, or 5, or 6? Well, let's look at one way that we could, still in the plane, use vectors to encapsulate the same information. I claimed that I could write the line this way. That's not a P, that's an L. I know, it looks like a P.
Oh.
Changed it into an L. They just outlawed that in California.
What do you mean?
How does it not write this thing?
I can write it this way. 2, 3 plus t times 9, 2. Now, why is that the same? What did I just do? Well, this 9, 2, that's just delta x, delta y for that point. So geometrically, what I'm saying, here's 2, 3, and here's the vector 9, 2, which happens to go all the way up to 11, 5. So I took the vector between those 2 points. And to get any point on this line, I could just take any multiple of that vector I want, as long as I start at 2, not 3. So it's an initial point and a direction. That's what a line is. And so that hopefully makes sense geometrically. Now we'll verify algebraically these are actually equivalent segments. So to do that, I'll write the equation of the same line, little l, in parametric form. My x component is 2 plus 9t, and my y component is 3 plus 2t. It's the same thing I've written with vectors. I just expanded to parametrics. Now, how can I make this look like that? Well, there's an extra variable, it's t. So let's eliminate it. So I'll do that here. I'll say t is x minus 2 over 9. And then plug that in there, plus you. And I get y minus 3 is 2 times x minus 2 over 9. Which, surprise, surprise, is the same as that. So by eliminating t, I was able to get an equation relating x and y, which is the same as the equation of my line. So what I just did here, what you learned in Algebra 1, doesn't really work in higher dimensions. There's no real good way to scale this. But this does. This scales just beautifully into multiple dimensions, because your equation of the line can look like this. Line as a function of t is some initial point plus t times P2 minus P1. And let's draw this as a picture. Right, this is a line that goes through 2 points. So there's P1, there's P2. P2 minus P1 is just the vector that goes between the two of them. The content of this equation is that any point on the line you can get from starting at P1 and adding any multiple of this vector. So you could go out to here, or you could go down to there, and that'll be a point on the line. Which is the same thing I did over there, right? Delta y and delta x 9 comma 2 is just P2 minus P1. Now, is there anything in this equation that restricts us to 2 dimensions? No. This point could have 15 coordinates. And as long as I had 2 points in the same dimensional space, I could write an equation for the line. So that's pretty cool. Now let's write the same thing in terms of parametric equations. And the notation for this is a little onerous, but it's good for us. And I won't do a lot. We won't do a lot of equations in this level of generality, but I will when I can. So what's going to be messy here? Well, in 2 dimensions, our variables are x and y, and 3, x, y, and z, and even in 4, you can do x, y, z, and w. But in n dimensions, I kind of run out of letters. Right? There's no way I can easily.
Greek symbols?
Huh?
Greek symbols?
Well, no, because then you still run out, right? So there's only 26. Well, yeah, we're going to call our coordinates x1, x2, x3, x4 with superscripts. So my coordinates are x1, x2, x3.
So there are going to be more than 24 variables in this group that you're showing?
Well, there's n, right? I'm
Infinite.
It could be infinite.
going to put down 1, 2, and then some dots, and then
Wait, but why just would, why are these superscripts on subscripts?
because
Details.
subscripts distinguishes between different points. Those are coordinates, so this, you should think of this is like x, y, z.
We can't use X, Y, Z, W, because they're running letters.
Doing right.
So you're just doing this for parametric?
And I'll show you what the first one is. So if I expand this over here, what is P1? It's just an x1, and an x2, and an x3, all the way up to xn1. So the subscripts all mean that it's the first point. The superscripts are telling you what coordinate. And the same thing here with P2. It's an x1, 2, x2, 2, x3, 2, all the way up to xn 2.
So it's just X, Y, and Z.
That's just x, y, and z. The first x, y, z, and the second x, y, z. So my x1 coordinate is going to be the first point over there, which is x11 plus t times x21 minus x1.
Wait, so x1t is like f of x.
Yes, x1 of t is like f of x.
What are those little letters on the last numbers on the last one? Thanks.
It's a subscript is position. How did you define that?
No, subscript is the point. I have 2 points. First point and second point. Now, I know this is what I want you to do now is fill in what would the x2 be? What changes and what stays the same?
x1 plus t times x1 minus x1.
I don't know if you were reading the numbers from that time.
Oh, I got it.
It's P1 is
Just
X1,
the one.
2, or is it X1?
All the
Is it
bottoms
X?
are plus
Well, this
one.
is, P1 is just those coordinates.
So it's x21 plus t times
P2 is
x22.
those
minus
coordinates. That's just P2.
Read the bottom. X1, 2. X1, 2 plus T of X, 2, 2 minus X, 1, 1.
Do you
Yes.
read bottom,
He's
top?
You should, well, normally you go from top to bottom.
Okay,
But
okay.
that's,
So we,
So it'd be x21 plus t times x22 minus x21.
yes,
Oh.
yes. Because which point it is, right, it's the first one plus the second one minus the first one. But which coordinate am I looking at? I'm looking at coordinate 2. And then some dots, and all the way down to x superscript n. That's going to be the same thing, the first coordinate plus the second one minus the first one, or the first point plus the second one minus the first one, but the nth coordinate. So that's my nth axis in n-dimensional space. And that's the parametric equation of the line.
What is this? Define
X, Y, Z. So it's which axis you're on, or which dimension.
So it goes x1 of the x-axis,
X1 is the x-axis.
and then x2 is the y-axis.
Z-axis. Yes. And there's nothing easy about double coordinates, right? This is tricky. Then you can get into worse, but we won't. At least not anytime soon. Now, I'm going to take that same idea and just write it for x, y, and z, just so you can kind of see a simpler version. So that's x1 plus t, x2 minus x1, y1 times t, y2 minus y1, and z1 plus t, z2 minus z1. So that's the same thing, I've just gotten rid of the extra level of abstraction. So that's still the same thing, still parametric equations. But the reason I did this is I'm also now going to show you the symmetric equations of a line, which I could do over there, but it starts to get a little bit slow. So the symmetric equation of a line is another way of writing the same information. And look at this first equation. I can solve for t here, right? And in 2 dimensions, I just took that t and plugged it into there and just got one equation. Well, I could do that here, but I'd still have 2 equations. And if I took that t and plugged it in there, I'd still have 2 equations. So if you substitute and keep plugging in, that doesn't really help any. But what I can do is this, I can solve this for t, and this for t, and this for t. And since they're all t, I can just set them equal to each other.
What the?
Okay, I officially don't have the weirdest
Barney.
sneeze.
Burning with fire. Fire. Get your memes right.
Jesus.
That looks like a firework.
This will be not killing us.
So here's,
It's on video, or at least audio.
here's the symmetric equations. X minus x1 over x2 minus x1. That's going to equal y minus y1 over y2 minus y1, which equals z minus z1 over z2 minus z1.
We can abstract this.
Yeah, and then obviously that same thing would work over there, which instead of x, y, z would just be x11, x21, and all of that.
Yeah.
And this is an equation of a line. The symmetric equation is kind of weird because it has 2 equal signs in it. Right? Usually equations don't come with 2 equal signs, but it says this is equal to that and that is equal to that. You can't discard any piece or it's incomplete. So let's do an example of all this. Let's find, in just 3 space, let's find the line through 1, 3, -2, and -4, 2, 0. And using my notation over there, I'll call this first point P1, and second point P2. So you should picture in your head, here's P1, here's P2, and here's the vector between them. So I'm going to say P1 plus any multiple of that vector. So the line is going to be P1, 1, 3, -2, plus any multiple of what's the first term in this vector?
-5,
Bingo, because it's the change in x.
-1 and 2.
Bingo. So that's the vector equation rule.
Oh.
Now we could write the parametric equation. X would be 1 minus 5t, y is 3 minus t, and z is -2 plus 2t. The rest.
Algebra.
Algae.
It's like an algae.
Yeah.
It's
Everybody got it, everybody.
And there's the symmetric equation of the line. By solving for t and just setting them all equal to each other.
That top thing next to the Z is a 2, right?
That is a 2. Yes.
Oh, 2 look different. And like all these 2 look the same.
Right.
Gosh,
Get a new hairdo and
Oh!
at least he knows you're
It's
good.
just a connection.
we were doing a good question. She's exactly right. Questions? Others? People with normal hair? Boring hair?
Awesome.
What?
My hair is exhilarating.
Did you say your hair is exhilarating?
Good feeling.
Okay, so notice that the equation of a line in whichever format you put it,
Wait,
it only has one independent variable. There's only one independent variable.
how do you find the slope of this?
That's my next question. You're in the right place.
Look at the future.
The equation of a line has only one independent variable. Now, what do I mean? Well, clearly here, the independent variable is t. And here, the independent variable is t. Like, once you pick t, then x, y, and z are determined. Over here, I've eliminated the t, but there's still just one independent variable, because if I pick a value for x, then I can solve for y and z. And then symmetrically with all the other variables. So I only have the freedom to pick one value. And once that value is picked, everything else is determined. So one independent variable, we can call this, borrowing a term from physics or mechanics, that this system has 1 degree of freedom. There's one thing that I can change. Everything else is determined. No matter how many dimensions I'm in. No matter how many dimensions I'm in. Therefore, a line is equivalent to one-dimensional, we'll say a one-dimensional say one dimension of freedom. One dimension of freedom equation. It's equivalent to, like, you can take it as a definition. So this is one way I can define a line. No matter how many variables I have, or regardless of what the dimension of the space is, if I have an equation or a set of equations, there's only one dimension of freedom, there's only one parameter that I can change and everything else is fixed, and that's all. Now, technically, this definition doesn't just limit us to linear lines, it could be, a curvy line. But still, curvy lines, there's only essentially one parameter, and we sort of saw that last year in BC, that you can take the parameter of a curve as being your arc length. Whatever distance you are from your original point is your position on the curve. So, using this definition, how could I define a plane in higher dimensional space? Yeah, as long as you have 2 degrees of freedom, if you can change x and y, that's going to be a plane. Or actually, it'll be some kind of surface. It doesn't necessarily have to be flat, but some kind of surface in however many dimensions you're in. 2 degrees of freedom. So that's the equation of a line in higher dimensional space and a 3D example. Now let's look at Mohini's question. What's the slope of this thing?
Mr. White,
Yeah,
is that supposed to say 1 degree of freedom equation or 1 dimension?
same
Same thing.
dimension of freedom, degree of freedom.
Exactly, okay.
Yeah.
Same.
What's the slope? Well, let's,
Wait, so before we go on,
yeah,
like, I don't really get like the significance of the t next to like t negative 5 negative 1 2.
it's your parameter. I mean, you can think of it, not exactly, but,
Like in the parameter equation, I understand you plug it in as your one variable, that's how you get the equation, but like
and its significance is it's sort of like the distance from your starting point.
the magnitude.
It's not exactly the magnitude, because this would have to be a unit vector, but if this were a unit vector, then t would be exactly the magnitude.
Right, but why do you need a t if you already know like a specific point that is in a 3-dimensional space? Like you know it's anyway, it's an equation.
Well, without the t, then I just have a point.
Team needs to take other points.
So if I gave you a t, you could tell me what point was on the line. Conversely, if I give you a point on the line, you can solve for t. So there's a 1-to-1 correspondence between the value of t and points on the line.
Alright, so for that one you give us 2 points and with those 2 points we can find p, which is the line.
Okay, so what's the slope of that thing?
Isn't just
So t equals,
Isn't it just see that?
t equal to 1 and then.
it's just it multiplies the
No, but it's
Well, pick a t value and
Does that make sense?
go from there.
Okay, so let's pick a t. Let's say if t equals 1, then I'm going to get negative 4 to 0.
It's 1/5.
Wait, can you just do this one?
Well, what does slope actually mean in 2D? What does slope mean? What's the definition?
Of y over x, so the
Right.
change.
Or let's use differential notation because it's going to be the same thing for us. It's dy over dx, right? That's the slope. Well, what else? What other terms up here now that I have 3 variables? What other ratios can I consider? dy over dz,
dz over
dx over, yeah, right? And I've got, well, essentially, let's just say these 3 because the reciprocals of those would be the other. So in some sense, as soon as I jump from 2 dimensions to 3, all of a sudden, now I have 3 slopes to worry about. 3. And, I mean, does that make sense? I mean, think about a road, okay? You can be going up a hill. So there's definitely a slope going up the hill, but the road can still be level, right? Without a tilt to the left or the right. So if I asked you for the slope of that road, well, it would depend on which way you're measuring. If you're measuring straight up, you might be like, oh, well, the slope is 2. If you're measuring straight across, you'd say, oh, the slope is 0. Because I can walk, straight across this road without tilting at all. And then if you measured at some angle, you'd actually get something between those 2 values. So slope gets a little bit more complicated in higher dimensional space. But we can definitely talk about these things as one way of looking at slope. So let's take our same line again. It's basically 1, 3, -2 plus dx, dy, dz. Where dx, dy, dz is just those points over there. So for this particular line, dy over dx is 1/5. So if you look at how much y is changing in relationship to x, it's pretty flat, 1/5.
Or if you like just set them equal to each other and find y equals all that. Because that's what I did, and I got one thing, when I set one shape, I got y equals.
And basically that's what you're going to get when you set them all equal to each other and cancel out the other variables. You're essentially losing information. You're losing information about z. So the 1/5 that you got was correct for the relationship between x and y.
Yeah.
That's right. And if you did it the other way and eliminated x, then you could get the relationship between y and z. dz over dx as a slope is -2/5, and dz over dy as a slope is -2. So on this line, its slope, you know, how much of an angle this line has really depends on sort of which axis you're looking at.
Is there a reason why you chose the PV on top?
Not really. It could go either way, but often, you know, usually you'll write z as a function of x and y. So that's why I was preferring dz, but that's
It doesn't just those top three are the same thing.
exactly just recently. Okay. And it turns out that this concept of slope is not really what we're going to end up with. For lines, we're going to go for something that scales a little bit better. Because this, it's kind of, well, this is not the kind of definition we're going to use. But if we wanted to look at a natural extension of the concept of slope, this would be it. So I can have multiple slopes. If I was in 4-dimensional space, there'd be 6 of these. Right? Because 4 times 3 is 12 different pairs, and half of that is 6. You know, in 10-dimensional space, there's 45. Basically, it's going to be n choose 2. Is how many different pairs of slopes I'm looking at. So it quickly starts to become
How did you get 45?
10 times 9 over 2.
It's ridiculous. 9.
Formula for n choose 2. Pascal's triangle.
Oh, gotcha.
Right? That's
Okay.
10 and the 9, but then they're in pairs. So
So in 10 dimensions, there's 9 spots.
Right.
And so you have,
Right, good. So this concept quickly becomes unwieldy, and it also turns out that it's a little bit redundant. Because knowing all 3 of those values, I can actually recover, you know, one of the values from the other 2, or 2 of the values from the other one. So here's another way of looking at slope. If you think about the polar equations in 2 dimensions, instead of x and y, we have r and theta. And there's a relationship between theta and xy, right? Because we have this formula, you know, theta is arctan of y over x. Where if that's my line, theta is the angle between the line and the x-axis. This idea scales very nicely to higher dimensional space. It's kind of hard to draw the picture. It's very hard because it's hard to draw lines because there's really no perspective. But here's my axis, x, y, and z, and that's a line. Let me make it a little bit linier. Let's say there, there, there. Okay, there's a line.
So it's like coming
I
towards
can
us.
dig it.
It's coming, yeah. So X, Y, Z, it's kind of coming out, right?
It's the coolest trick.
And this is where the 3D Pythagorean theorem might go.
Maybe the 3D Pythagorean theorem might have something to do with this. Yeah, we won't use it for here, but same pictures.
Okay.
Okay.
Oh, it's like
I can define or measure, if I had an actual model of this, I could measure the angle between my line and the x-axis. Because the line and the x-axis, they just form a plane, because it's two lines. So ignore everything else, put a protractor and measure from there to there.
So it's like, they're like this, and you want to measure that.
Exactly. Okay.
There's like this. Sure.
You know what I was talking about?
Sure.
I can also measure the angle to the y-axis, call that beta, and the angle to the z-axis, and that's gamma. Gamma looks a little silly y. Those are called the direction angles. Or actually, and we'll see why they're called this in a minute, although you might be able to figure it out yourself, or direction cosines. Why cosines? Because don't I have a nice little formula for that?
A squared plus b squared minus 2
Well, that one, but I have a nicer one. Formula for the angle between two vectors.
well, I just said that.
Wrong.
Cosine of theta is a dot b.
Oh,
Okay.
okay.
Magnitude A, magnitude B. So since I have, so the reason they're called direction cosines is a lot of times instead of actually giving the angle, we just give the cosine of the angle, so you don't have to do the whole inverse trig step. But the cosines come from there. And now the nice thing about this is in 20-dimensional space, I'm only going to have 20 direction cosines. I don't have to worry about 190 rates of change with respect to different pairs of axes. And so keeping with this same example,
Wait, so use like A as your axis and then B as the line you're measuring, and then you can, like what? Like how do you use that with
Yeah, with the
with one plane?
well, yeah, I'll show you. That's what we're going to do. That's what we're going to do. So my same line, which was 1, 3, -2, plus -5, -1, 2 times 2. That's my line. Alpha is the angle between my line and the x-axis. So if I take a cosine of a dot product, one of those vectors is going to be the x-axis, which is 1, 0, 0.
Can you say that one more time? Can you say how you got that one more time?
Well, if I want to know the angle between a vector and the x-axis, one of the vectors is the x-axis.
Oh, okay.
Yeah.
Oh, so you're cutting out to.
And now my other vector, what am I going to take? This is the equation of the line. What am I going to take the dot product?
The 1, 3, -2 times
No, the
-5. Yeah.
that.
Now that may not be obvious, but if you think about the slope of a line in 2 space, the b, the y-intercept doesn't matter, right? For the slope, this is kind of like your y-intercept. This is where you're starting. So the 1, 3, 2 doesn't matter. All the slope, all the rate of change is happening right here. And I just need the magnitude of this thing. So I take the dot product of my direction,
So
Those-
again, where are you getting the 1, 0, 0?
that's the x-axis.
Oh. Okay.
Okay. Now, this dot product's easy. What is that dot product? Just -5. Over, well, this is 1, and that's going to be root 30. So cosine alpha is -5 over root 30.
How the heck
Yeah.
did you
Where's
do
the numbers
that?
come from?
From there,
But where did you get -5 and 30?
Yes, I just did the one, the other two.
well, this is the dot product.
Okay, that's A dot A.
Oh, you did,
B
oh,
dot B
okay, you
plus
did all
C
that.
dot C.
Okay, that weird.
Oh, you just did that on your head.
Oh, because,
It's literally -5.
Oh.
5 plus 0 plus 0, yes, I did that in my head.
30 is, the 30 is -5 squared plus.
why did you square -5?
It's
That's
square.
the formula.
It's square.
To find the magnitude, it's literally a squared plus b squared, c squared.
So, okay.
Like, you know, like the formula x squared plus y squared plus z
I'll
squared.
show you, I have it written down.
That- that's-
25, 26, 27.
I'm sure it's faster.
Oh, I got you. We're good.
What is that?
That's a cute little.
It's the distance formula.
For
I
magnet.
don't know. What are these symbols?
The symbol that this is for
Yeah,
you.
Beta,
the
yeah.
line with the.
It's just,
What's the name of that?
what is cosine beta?
Yeah.
Oh, right.
So you're under.
And cosine gamma.
Oh, 80.
Because when you take the dot product with the y and the z axis, it's going to isolate the y and the z components of your vector. Everything else is the same. So my direction angles for this line, the angles that it makes with the axes are the arc cosines of these three numbers. And often we don't do the arc cosine step. We just say, the direction cosines are this, and that. Because for a lot of the problems, that's all we need. So with that,
Okay, so I'm about to say something that might be really stupid.
Just.
But if you're, no, it's not this question. So if you have the cosine of alpha equals -5 over 30, is that like adjacent over hypotenuse, like is the hypotenuse of this thing through 30, and then that's x, and then y would be like, does it work like that?
sort of, because the length of this vector is root 30, so you can think that as the hypotenuse,
Okay,
right? And -5 is the x component. So
okay,
you could think of, if you actually drew it in 3 space, you could draw a triangle just on that side that had root 30 here, and the x component was the adjacent.
okay,
Then you could draw another triangle in the y direction, another triangle in the z direction.
okay,
So that's absolutely a valid thinking.
okay.
Yes.
See, if you give a disclaimer, it doesn't sound so.
Maybe you should always give this to me.
I feel like that means that she's thinking it through more.
Yeah.
She's realized
Oh,
that.
maybe this
That's
is.
what
If you cover that, and then you realize you shouldn't have been, you just don't say it.
Thanks, guys.
That's a good idea.
Question, is this the same line?
No. Yeah, it is.
Right, because I just scaled this. Same line. Question, what's the magnitude of this vector?
1 over square root 30 small. It's, oh yeah, it's not, wait, it's square,
Over square root 30 is.
It's the square root of 25, 30 minus 1/30th plus 2 plus 4/30.
well, you don't know, you don't know.
Square.
You don't
Negative
know.
1 over 6, and then negative 1 over 30, and then 2 over 30.
That is what I just said. Thank you very much.
That's okay, you're wrong. Wait till it.
That's what I just said.
Oh, that's one.
Right, because if you divide a vector by its magnitude, then you get a unit vector. So this is a unit vector in the direction of the line. And notice when this is a unit vector, then this is just cosine alpha, cosine beta, cosine gamma.
Wait, that's equal to cosine?
Equal to, because when I take the dot product, it's just going to pick out that first number.
Okay.
And both of these magnitudes down here are 1. So when this is a unit vector, you can read the direction cosines right off it. Question? Maybe? So. And we'll finish up this little piece by talking about the plane again, because this works with planes too. So I could write the equation of a line in 2D is just cosine alpha cosine beta. If this is true, right, times t. And that would be a line that went through the plane. Or, sorry, that went through the origin. And alpha is the angle that it makes with the x-axis, beta is the angle that it makes with the y-axis. In the plane, and in the plane only, alpha plus beta is 90 degrees. So cosine of beta is equal to sine of alpha. Because they're cofunctions, it's a cofunction identity. So that means L is actually cosine alpha sine alpha times t, which is cosine sine alpha cosine alpha. And if this is dx and dy, then the slope is dy over dx, which is tangent of alpha. Which recovers our original polar equation that theta is the arctangent of y over x. dy over dx is tangent of alpha. So in 2 dimensions, this simplifies to only needing one direction coefficient, because once you know alpha, you know beta.
Well, in
Wait,
3
if you were
dimensions.
But in 3 dimensions, there is no such, well, there, I mean, you can, but there's, if you know,
Not all the,
because you could have an angle with the x-axis and the y-axis and the z-axis separately, and you can move each one of those. Well, it turns out there's one less degree of freedom than it seems like, but still, one doesn't completely determine the others. All right, questions? Okay, I'll do a little bit about planes, which is next. Today's kind of a big notes day, but that's it for lines.
Does anybody
now
know
we're
what
going into
time?
circles.
Now we're going to planes.
Does anybody know what time the
Yes,
postman
because
period is on
planes
Friday?
are.
You are in.
I guess it like sucks.
This is the
4:45, you think it takes 15 minutes to get you guys ready to go before you, as taking a bus? Probably 5:45.
Yeah, that sounds like many. You guys 15 minutes, you get ready to get on the bus and be at the 3:05. Pretty slow. Pretty slow.
How do you get 0 to that?
This is the vector that you want this one. Oh, okay, so like,
It's not a pretty rectangle.
so if it's like,
Yeah, of course. You.
Okay, planes. Here's a plane coming at you.
No, clever. By the school. What school is that by?
This plane has 2 lines in it. Let's pick any 2 lines in the plane that intersect, have a common intersection. So as long as they're not parallel. Take any 2 lines in the plane. What we want to do is we want to try to write an equation of a plane. And we'll start in 3 dimensions, but really it's not as complicated.
There's just something.
So geometrically, we can all envision a plane and kind of have an idea of what it means, but what it looks like. But how can I turn this into something that I can get an equation? Well, here's one of the more natural ways to do it. Take any 2 lines in the plane, have them intersect, and find a line perpendicular to both of them.
where are you trying to find her?
The 3D line.
So like you've got 2 lines here and you want the line that goes like, oh, goes that way?
Oh, it's coming to me.
Yeah.
Wait, how's the?
Right.
how's
No, it's
the-
up going up.
It's going up.
Like this.
Well, that's
Like
right.
the line's coming out.
Yeah, so it's like you got
It's
inside.
like, if you look at a flat.
It's like the X, Y, and Z
Yeah,
axis.
you have 2 this way, one like.
This.
Yeah.
And so what are we trying to find right now?
Trying to find the lines perpendicular to those 2 lines.
But you need an equation.
They have to have the negative reciprocal slope. Bam.
Both of them. Wait.
But that's
There's no such thing as single planes.
Yeah, exactly. It's all.
There is no such thing as.
Wait, so this.
N is called the normal vector or line to the plane.
Yeah.
And N satisfies the following equation. We talked briefly about cross product a couple weeks ago.
Oh, that's good.
When you take the cross product of 2 vectors in 3 space, the 3rd vector you get is perpendicular to both of them. That's one of the properties of cross product that we saw. So this is perpendicular to L1 and L2. Now, does n, the normal vector, does it depend on which 2 lines I pick? Will it vary from line to line?
Yes.
No, wait, line, what do you mean line,
Yeah.
like line 1 from line 2 or like any line?
It will never change.
No.
It shouldn't change.
It will never,
Yeah,
ever
is that a
change.
different n?
No.
Never change.
No.
Because the plane's flat, right? So that normal vector, it'll start in a different place, but it's pointing in the same direction. It's the same vector.
Unless you angle the plane, then it'll change. The plane's just.
It's, plane's fixed.
plane's
So
fixed.
the plane's fixed. So the normal vector, regardless of where you position it, right, whichever 2 lines you pick, the normal vector's going to be pointing in the same direction. So the normal vector is maybe something I can use to write the equation of the plane. There's no vector, it's x, y, z, it's just 3 numbers. Maybe I can use that fact. Well, before I develop an equation, we'll kind of do an example to work through what these formulas mean. So let's take these 3 points. 1, 2, 1, 3, 4, 5, 7, 10, 3.
Is that here? Like example here?
EX example, yes. I want to find a plane through all 3 points. And we'll just do this very deliberately, sort of following that idea, and hopefully that will help motivate an equation that works in general. So if I have these 3 points, L1 and L2, I can just define them. L1 is basically from A to B, and L2 is from A to C. Like, that's arbitrary, but that's what I'm going to pick my L1 and L2 to be. So in this case, that makes L1 is going to be 2, 2, 4, and L2 is going to be 6, 8, 2. So it's just the displacement vector between A and B.
No, 10 minus 2.
Yeah.
So how can I find the normal vector to the line?
Cross product.
So IJK 2, 2, 4, 6, 8, 2.
Oh gosh. I didn't like it.
It's going to be negative 28.
Yeah, we can all just pull this out.
What's the negative
4 minus 32.
Just kidding.
So that's the normal vector. And to simplify it, I'm going to pull out a 4 because it's still the same vector, right? Same direction, just smaller numbers.
Wouldn't it be negative 20?
No, because remember, it's the middle one is minus.
Oh. Do that.
It's okay, I'll go too.
What, that wasn't even.
I was just asking a question.
There, like freaking like dump on her every time he gets there.
Okay, so that's the normal vector to this plane.
Yeah.
Well, it's still not an equation. I want an equation for the plane. So I'll sort of copy my little picture over here. Here's my normal vector. Now for this to be an equation, I should be able to take any point, x, y, z, some point in the plane. I need some equation.
So it's getting off the plane?
No, x, y, z is on the plane.
Then why is it actually coordinates?
So,
Because if it's on
It's in 3
one-
space. Right? It has 3 coordinates. There's only 2 degrees of freedom, but it still has 3 coordinates.
Okay.
Right, 2
Because
degrees
there's
of
1,
freedom.
0.
And here's what I can do. Let's imagine this normal vector here is living at point A. So I know its coordinates. And x, y, z, I'll just call that point P, just give it a name. So let's draw the vector between those two. A and P. What can we say mathematically or geometrically
It'll be perpendicular.
to the normal vector? Exactly. AP is perpendicular to N. And that's enough to write an equation.
Wait, so what we did was we had to find a plane that goes through ABC. So we got 2 lines for ABC, and
Yep.
then we just found a line that was perpendicular to both.
Yep. And now I'm taking basically 2 more points. A point that I know that's on the plane, which can be any point that's on the plane, so I'll just pick one of those 3. A point that's on the plane, and then my x, y, z. And I know that that vector, that displacement vector, has to be perpendicular to n. So if AP is perpendicular to n, that means that AP dot product n equals 0. But I know what AP is. It's the displacement vector, so it's x minus 1, y minus 2, z minus 1. That's just taking p minus a. But I know what n is. So I can finish this up here. We're almost done. X minus 1, y minus 2, z minus 1, dot product, negative 751. Equals 0. That's an equation. We'll multiply it out, make it more standardized, but that's an equation. It relates x, y, and z. If you pick x and y, I can tell you what z is. 2 degrees of freedom. Right? You can't just pick x, because then I'm still stuck. And you can't pick x, y, and z, because it may not be a solution. But if you pick x and y, I can solve for z. This is the plan. Let's multiply this out. That'll be negative 7x plus 5y plus z equals, I'm going to do all these others. 7 minus 10 minus 1, then negative 4. Or instead of equal to 0. That's the equation.
So that's n?
No, that's the
AB.
equation of the plane.
Oh, the whole thing.
The whole thing. So if we did our math right, A, B, and C should all satisfy this equation.
Negative 7 plus n. No.
And if it doesn't, check them.
Okay.
And then any other solution to this.
Minus 4?
Yeah, it should be
minus 4.
plus 4.
Oh, it's plus 4 over here. Thank you.
Okay.
Thank you. Yes, 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 yes.
That, you can tell.
Yeah, so now it works.
Who is it?
Do I know who it is? Oh, it's the person. Oh,
I'm gonna text her now.
So how can I
That
use
was
this?
stupid.
Girl. Push back like girl.
How can I use this idea to get an actual equation in general? Well, we don't have to do much. We just don't have to plug in any numbers. So here's the equation of a plane. Here's my plane, same sort of picture. And I can define a plane with a normal line and a point, I'll call it R, because that's what your book uses, just because. So this point is R0. So the equation of a plane, what do I need? I need a normal line and I need a point. And if you have a point and a normal line, you can define a plane. Now think about that. That's kind of like, there's actually a term for it. It's called a dual. It's the dual of a line. A line, you need a point and a vector, right? But the line is everything on that vector. For a plane, you need a point and a vector, but the plane is everything perpendicular to that vector. So if I follow a vector, that's one dimension. If I take everything perpendicular to that vector, it's 2 dimensions.
Oh.
So it's the same starting information, I'm just defining it, I'm using it differently. So here's how I can get the equation of a plane. Let's say there's some point R, which is x, y, z. An arbitrary point R on the plane has to satisfy that property that it's perpendicular to n. So n dot r minus r0 is 0. That's the equation. I can write this in a slightly different way. I could expand this and say n dot r equals n dot r0. Same thing. And we'll do an example now where I'll just give you the normal vector and a point, and we'll write what the equation is. Because if I gave you these three, then you could find n the same way we did here. For this one, let's take n as given. And the point as given. And let's just say, example, let's say the normal vector is negative 2, 5, 1. And it goes through the point 1, 2, 4. Well, R is going to be x, y, z. So my equation says n dot r equals n dot r0. N dot r is n dot r0. Well, this is super easy. N dot r is negative 2x plus 5y plus z. N dot r0 is negative 2 plus 10 plus 4. 12. Right, positive. And then just bring it over. So negative 2x plus 5y plus z minus 12 equals 0. That's the equation 12. So it's really not any harder than if I give you a point and the slope, write the equation of a line. Here I'm giving you a point and a direction vector. Here at the equation. The end.